Okay, so the plan for today is to um, finish up chapter 2 with 2.5 prime factorization and the least common multiple, and then start chapter 3 with introduction to integers. We're running a little bit behind schedule. We were slightly behind before, and then I had to cancel last Thursday's class, so that put us a little bit behind as we're coming up to the Unit 1 exam. So the material in the Unit 1 exam won't be all the way through Chapter 3. That was kind of what it was originally tentatively slated to be. But in the next day or so, either today or tomorrow, I will post a sample exam on WebAssign as well as an announcement clarifying exactly what the material will be. It'll kind of depend on how far we get today and then what I feel like we can comfortably get through on Thursday. I'm kind of thinking through sections maybe 3.2 and 3.3, addition and subtraction of integers. I think that might be a comfortable place, but I'll kind of confirm that when we wrap up today. One little detail, one change for the first exam is for this Unit 1 exam, we're not going to be using ProctorU. As I mentioned earlier in the course that we switched from Examity to ProctorU from the summer to the fall, and we have had a couple instructors have minor problems with some students for ProctorU. Some students were having trouble getting the tech to work out right. And as I was about to kind of check in with our kind of, point person, let's say for ProctorU for CCAC, I went to send him an email over the weekend and it said that he's going to be out on vacation this week. So I thought, it's probably not a good idea for me to try to post like I would have posted a ProctorU practice exam so that everybody could get in and work through it this week, but probably not a good idea to do that while our point person for that tech is out and then rely on ProctorU to be up and running and functional for everybody next week for the exam. So just the timing didn't work out great with this changeover and these kind of tech changeovers. There's always a little bit of rockiness, uh, on the first exam. So no ProctorU for the first exam. It will be kind of on the honor system, but I do strongly recommend um, kind of taking the exam honorably, taking it, um, you know, the within all of the parameters set for the exam. So things like no external aid, nobody helping you or anything like that. You might be able to boost your grade a little bit on the first exam if you worked outside of those parameters, but that's really setting you up for failure for the upcoming exams, for the final exam. Not to mention the kind of integrity hit that I don't think anybody really wants to know that they got a decent grade by cheating on an exam. You want it to be reflective of the work that you put into the course. So I think, in the long run, ProctorU will be here for the remaining exams for the course. We will have that up and running. It was just the time situation didn't quite work out for this first exam. Um, so I would strongly recommend taking the exam the same way that you're going to take exams 2, 3 in the final, and as if, ProctorU was on. So are there any quick questions before we jump into the material? Okay, so keep an eye out for the sample exam posted. The sample exam will be very similar to the actual exam. So the purpose of the sample exam is for you to sit down, take it as though you were taking the actual exam, um, and use it to diagnose anything that you might want to fix. If you go through the sample exam and you're happy with your performance there, you felt comfortable with everything, you were happy with your score, then you're probably ready to go for the actual exam and don't have to really do a whole lot of work. If you go through the sample exam and you're not happy with your final score, or there was a problem type that you really struggled with that you didn't expect, maybe going back and reviewing that problem type or digging into, okay, what did I get wrong on the exam? Was it just that I was making kind of silly mistakes that if I just am a little careful, if I just slow down a little bit, I'll be able to do better? Or was it like I misunderstood this whole topic and I want to review that topic, so using the sample exam as a self-assessment, and if you do identify some things you want to fix, maybe going back, reviewing that material, doing some extra practice problems, and then retaking the sample exam after that to see if you've kind of remediated those weaknesses that you had identified. So that's how I would recommend viewing the sample exam, as more of a self-assessment. I definitely don't recommend going through the sample exam and saying, okay, here's problem one. I forget how to do that. Let me look up how to do that. Okay, I got it right. Here's problem two. I kind of forget how to do that. Let me look up. Right. If you do that, since you're not going to have that available on the exam, um, that's gonna make transitioning that knowledge to an actual exam setting very difficult. And again, that and the announcement will be posted either today or tomorrow, depending on, I'll write the exam after class today once I feel pretty comfortable about what material we'll get through on Thursday. And and I'll post an announcement just to very clearly say exactly what material will be on the exam. And I'll post the sample exam so that you have it available. All right, the quote of the day today is from the Roman lyric poet Horace, his satires. There is a mean in all things, too far to the right or left of which good cannot be found. So kind of like everything in moderation. I picked this quote for this week because in stats class, which was yesterday, we're talking about means and measures of center and things. So I thought it was just kind of cool that, that word kind of comes up here. And it also had a link to another course that I'm teaching, something that we're discussing in there. So um, yeah, so that's the quote for today, short and sweet quote. And then moving into section 2.5, prime factorization and least common multiple. And as I mentioned last time we met a week ago, I bumped a little bit of chapter or section 2.4 into 2.5. This bit on identifying prime versus composite natural numbers, I think it fits a little better with all of this discussion of prime factorization. Okay, so definition. A prime number is a natural number or counting number that's greater than 1, so not equal to 1, greater than 1, strictly greater than, whose only factors are 1 in itself. A composite number is a natural number greater than 1 that is not prime, that has at least one factor other than 1 in itself. So every number, 10 or whatever, has factors of 1 in itself. But if we were writing out all the factors of a number, some factors, like say 3, only have factors 1 and 3. Its only factors are 1 in itself. Other numbers, like say 4, it has 1 and 3 as factors, but it also has 2 as a factor. So it has at least one other factor other than 1 in itself. Why do we care so much about prime numbers? If you know anything about mathematicians, number one, they tend to care a lot about pi, and I'm not exactly sure why they care so much about pi. I mean, it's kind of cool, but you know, I think E is actually a better number, but that's a whole other discussion. But they also care a lot about prime numbers, and there is very good reason to care a lot about prime numbers. These comprise essentially like the building blocks, like the little Lego pieces that we construct really all of our number systems off of. They're the building blocks for the natural number system, and we build the rest of our number systems off of that basis. The whole numbers, the integers that we'll see later today, and the number systems that we'll see in the future, things like the fractions and decimals, and all of these things are built off of this natural number system, and this natural number system is built with the building blocks of prime numbers. And it's also important to note that the number 1 is neither prime nor composite. Our definitions of prime and composite numbers preclude 1. We say natural number greater than 1, so not including 1. So 1 is neither prime nor composite. Is that a huge deal? Probably not a huge deal, but it makes it so that, when we state theorems about prime numbers, we don't have to have all these special cases and say, well, except for 1, you know. So we just kind of define 1 to be neither prime nor composite. So we might ask ourselves, what is the only even prime number? Well, if I have an even prime number, that means that it has to be a multiple of 2, so 2 has to be one of its factors, and it can't have any other factor. other than 1. So what's the only even prime number? It's the number 2. Any other even number, say 4 or 6 or 10 or 20, is going to have at least one other factor. So what's the only even prime number is 2. Now we might say something like, well, what about 4? It has factor of 2 and 2. A repeated factor counts as another factor. So the only factor that we see here is the factor 2, but since it's repeated, right? So it has these factors. So 4's factors are 1, 2, and 4. So if I wanted to make any even number other than 2, I would have to multiply by something else, and then I'd have more factors, right? So I see that 4 has factors of 1 and 4, but also 2. So 2 is the only even prime number. All other prime numbers are odd. However, be careful with the direction of that statement. All other prime numbers are odd, but not all other odd numbers are prime. The number 6 has factors of 1 and 6, sure, but also say 2 and 3. The number 9 has factors of 1 and 9, but also 3. Right? So we can think of, especially for smaller numbers, we can list out just all the factors pretty easily. So any other even number other than 2 is not going to be prime. All other prime numbers other than 2 are going to be odd, but there are a lot of odd numbers. In fact, probably most odd numbers in some sense are not prime. Okay, so let's look at this example. Let's list all of the prime numbers that are less than or equal to 20. So let me give myself a little more space here. I'm just going to go through and list all of the numbers less than or equal to 20. And then we're going to go through and evaluate each one and think about whether or not it's prime. So if it's not prime, I'll cross it out. Maybe I'll cross it out in red just to make it clear. Well, right away, we can cross out 1 just based on our definition, because by definition, 1 is neither prime nor composite. So 1 is not a prime number. We confirmed above that 2 is a prime number, so we'll maybe write a check next to that one. What about 3? Well, 3 has 2 factors, 1 and 3. There's no other factors that 3 has, so besides 1 in itself. So that is a prime number. We discussed above that 4 is not a prime number. And in fact, we discussed above that the only even prime number is 2. We've already got that one accounted for. I can actually go through and cross out all of the other even numbers now comfortably. I had thought about this and I developed a rule that said, other than 2, all other even numbers are not prime, they're composite. Why is that? Well, because all other even numbers have a factor of 2 as well as a factor of 1 in themselves. So they have an extra factor other than 1 in itself, namely 2. So not prime. So I actually knocked out half of them roughly without even really having to think. I just used my general rule that I developed up here for even numbers, and that let me knock out a whole bunch of them. This kind of idea is called a prime number sieve. So we could go through and we could say knock out multiples of 3, 3, 6, 9, 12, 15, 18. Multiples of 3 bigger than 3 are all going to have a factor of 3 in them. So 6 has factors of 1 in itself, but also at least a factor of 3 in it. 9 has a factor of 1 in itself, and also at least a factor of 3. So I could actually knock out all of the factors of 3 and keep going. If you don't see why that is, that's not a problem. You could go through the method that we're going to go through next, but we could just go through and knock out all the factors of 3 as well. Maybe I'll cross them out like this just so it's clear. So we get rid of 9 and 15 almost for free that way. Now for the rest of these, I'm just going to investigate them and see what is the list of all of their factors. So for 5, 1 and 5 are factors. Is 2 a factor? No, 2 doesn't go into 5. Is 3 a factor? No, and now I've gotten up to where I'd just be repeating things. So if I did keep going up, 4 is not a factor and 5 times 1 is 5, but that just repeats over here what I already have. So 5 is a prime number. 7, I have 1 times 7. Does 2 times a natural number equal 7? No. 3, no. And since 3 times 3 is 9, which is bigger than 7, I don't have to keep going any further. So 7 is prime. And by a similar argument, 11 is prime, 13, 17, and 19 are all prime. So in fact, I can actually figure out the prime numbers less than or equal to 20 by just basically getting rid of the multiples of 2 other than 2 and the multiples of 3 other than 3. So that's actually, and getting rid of 1 just by definition. So that's actually sufficient for finding my primes less than or equal to 20. Now, if I wanted the list of primes less than or equal to 50 or 100, there would probably be some multiples of 5 or multiples of 7 or something that I would also have to knock out. But I don't need to worry about that. Right? This is probably going to be enough for our purposes for most problems. And if I really came up on a problem where I needed to know, okay, here's 37, is 37 a prime number or not? I probably don't want to include that in my list. I'll just kind of evaluate that when I need to. I'll just go through and find the factors of 37 and see if it has any factors other than 1 and 37. But I see my list is 2, 3, 5, 7, 11, 13, 17, and 19. At first glance, it actually seems like a lot of numbers are prime numbers, but this is kind of because when we're looking at smaller numbers, they tend to be prime numbers more often than when we're looking at larger numbers. In some sense, like, for a number to be composite, it has to have a factor of a number that's smaller than it, but not 1. And the larger the number you're looking at, the more numbers there are that are smaller than it that could potentially be factors. So that's kind of one way to think about it. So if I'm looking at the number 200, it has a lot of numbers smaller than it that could potentially be factors of it. If I'm looking at the number, 7, there are only a few numbers smaller than it that could potentially be factors. Okay, so these are our primes less than or equal to 20. So how do we determine if a number is prime? Well, we test each of the primes in order, so starting with 2, then 3, then 5, and going up to see if it's a factor of the number. We start with 2, stop when the quotient is smaller than the divisor, or when we find a prime factor. And if the number has a prime factor, then it's a composite number. If it has no prime factors, then it's prime. That's maybe a little silly way to say it because a number is always its own factor. It's always a factor of itself, but I think we get what they're trying to say here. Okay, for each number, determine whether it's prime or composite. So let's look at 53. So 53, what are some potential numbers prime numbers that could be factors? Let's get our prime number list back on the screen. I trying to get that out from behind those little markers. There we go. So the first one we might want to investigate is the number 2. That could be a prime factor. But we see that's not going to be a factor because 53 is not an even number. Remember the divisibility test for 2, if our number is even, if it ends in 2, 4, 6, 8, or 0. So 2 is not going to be a factor. Is 3 a factor? Well, our divisibility test for 3 was if we add the digits together, 5 plus 3 is 8. Is 8 divisible by 3? No, it's not. If the sum of the digits is not divisible by 3, then our original number is not divisible by 3. What's the next one it could be? Say 5. Well, is 53 divisible by 5? The divisibility test for 5 was if the number ends in 0 or 5. That's not the case here. Is it divisible by 7? Well, we said 7 and 11. I guess there are divisibility tests for those, but they're kind of they're quite complicated to deal with. It's easier just to investigate these individually. So I could either do a long division of 53, like 53 over 7, but that doesn't actually help much because I just have to figure out how many times 7 goes into 53. But 53 divided by 7, I know that 7 times 1 is 7, times 2 is 14. Again, if you're still not comfortable with your times tables, hit that a couple of times in the morning, a couple of times in the evening. Get used to the times table so you can count up these multiples pretty quickly. 7 times 1 is 7, times 2 is 14, times 3 is 21. We can keep going. We're still not at 53. Times 4 is 28, 5 is 35, 6 is 42. 7 times 7 is 49, getting close. 7 times 8 is 56, we overshot. So 53 over 7 is 7 with a remainder. 7 times 7 gives us 49, 50, 51, 52, 53, remainder of 4. 7 does not go into 53 evenly. So 7 is not a factor of 53. We can do something similar with 11. And I'll write out these multiples. I noticed that on consecutive multiples, I've skipped over 53 from 44 to 55. So 11 is not going to be a factor of 53. Do I need to keep going? Well, 7 times itself is 49. That's below 53. 11 times itself is 121, which is bigger than 53. So hypothetically, if I were to keep going and find a factor, that factor would be like just like the reverse of a factor I had found previously. But I haven't found any factors previously, so I can't find any going forward. So if I look at 53, it's not divisible by 2, by 3, by 5, by 7, by 11. It's also not going to be divisible by, say, 4, right? Why am I only looking at the prime numbers? Why don't I have to look at, say, 4? Well, because if it was divisible by 4, it would have to be divisible by 2 as well. Oops, I don't know why it jumped up like that, but right. Why aren't I looking at 6. Well, because if it was divisible by 6, it would have to be divisible by 3 and 2. And I checked those and it's not. Why aren't I looking at 8, 9, or 10? Well, because if it was divisible by 8, it have to be divisible by 2, or same with 10. If it was divisible by 9, it would have to be divisible by 3, but I already checked those. So again, I can really leverage this idea that prime numbers are the building blocks. And if I'm looking for divisibility, I only really have to check the primes, and that gives me a lot of other information kind of for free. I can skip over the composites because if my number is not divisible by the primes, then it's not going to be divisible by any of the composites that are made up of those primes. So 53, it is prime. So 53 was not a terribly large number, so we just kind of, started like using the sledgehammer attack, as I sometimes call it, just following our nose. What's the basic strategy? How can I just start going with this? A number like 1,773 is a pretty big number. I don't necessarily want to just, just start off trying to evaluate this number from first principles. I might want to think a little bit about this. There are a couple things about this number that I noticed. Number one, it's a bigger number, so I can go through a process like this, but if I just blindly go through it, it might terminate early. I might find a prime factor early on and be able to say, nope, I found a prime factor. It is a composite number, but I might not. I might want to think a little bit ahead of time and just ask myself, all right, well, number one, this is a bigger number. So I know that the kind of chances are, in some sense, that it's going to be composite. The prime numbers get fewer and farther between, the larger the number is. So if I really quickly just kind of think through my divisibility rules, well, one of the quick ones to check is the divisibility rule for 2 or 3. It's not an even number. However, its digits add to 18, which is a multiple of 3. So actually 3 is a factor of 1773. So 1773's factors are 1, 1773, 3, and probably a bunch of other things as well. But it has at least one factor that is not 1 or itself. So this is composite. This is not a prime number. Now, one unfortunate thing about finding prime numbers is, I suppose in some sense it's unfortunate, in other senses it's fortunate, that for a large number like this, if we didn't notice really quickly, if I didn't notice that it failed, or if it didn't fail, say, the test for 2 and 3 or 5 or something, and I had to start working my way up to, is it divisible by 7, 11, 13, 17, 19, and keep going for quite a while, because this is a pretty big number. It's going to take a while until I get to a number when multiplied by itself is bigger than 1773. There's really, at least in some sense, there's really no better way to check whether a number is prime or composite than kind of going through all the potential prime factors. On one hand, that's a little bit annoying for us, because if we want to, do a homework problem, that's can be a lot of computation. I would, be hesitant to assign a homework set where you had to, investigate some number like, a couple million or something like that, that wasn't clearly, say, an even number, where you can immediately say, nope, it's a number bigger than 2 that's an even number, not prime. Or maybe, see that it's divisible by 3 or 5 right away. So I would be hesitant to assign a homework problem like that. But if you were just given some number from some, something in the real world and asked, is this prime? That can be a tough problem. In fact, it's a tough enough problem that that question really underlies a lot of our cryptography, a lot of our security measures. If you log into your bank or something and you see the little padlock icon up there in the URL bar, uh, the basis of that, um, the mathematical basis anyway of that encryption system is our inability to efficiently factor large numbers into their prime factorization, or even to tell whether a large number is prime or composite. There are some funky special cases and things. There are certain types of prime numbers that you can easily tell that they're prime, but that's beyond the scope of this course. But kind of as a general rule, looking at a number and either telling is it prime or composite, or if it is composite, finding like all of its prime factors is a hard problem. It's a problem that we don't have a much better way to do other than just trying all of the prime factors and seeing which ones work. And kind of a random side note, but interestingly though, quantum computers can do this very quickly. So a quantum computer isn't like a really fast regular computer. Like the paradigm is completely different. So there's an algorithm called Shor's algorithm for quantum computers that actually turns this incredibly difficult problem in normal computers into an easy problem in quantum computers. And that's kind of a concern these days because, quantum computers are kind of becoming a reality. Now, the folks that have quantum computers these days, they have very little incentive to break into your bank account or something, Google or Microsoft or anybody, but um, who knows how long it is before we have quantum computers sitting on people's desktops and have to actually worry about this. Okay, so now that we can investigate whether a number, if I can select it, which I can't seem to do, whether a number is prime or composite. If a number is prime, we know what its factors are. Its factors are one in itself and nothing else. If it's composite, it can have a bunch of different factors. So I know that, for instance, 1773 has 3 as one of its factors. It could be written as 3 times something. And maybe that something is a prime number, or maybe that something could even be broken down further. Maybe it's a composite number and I could break it into more prime factors. That's what we're going to be looking at here. Finding the prime factorization of a natural number. The prime factorization of a natural number is the product whose factors are all prime numbers. So for instance, if I wanted to find the prime factorization of, let's say 12, I see that 12 is 2 times 2 times 3. That's its prime factorization. It's a product of numbers which are all prime. Importantly, the prime factorization of a natural number is unique. When I break this number 12 down into its kind of multiplicative building blocks, the way it breaks down is unique. Everybody, every time, will find 2 2s and a 3 up to rearrangement, right? I could write 3 times 2 times 2 or 2 times 3 times 2. So up to rearrangement because multiplication is commutative, but we're always going to have the same number of each prime number represented. So I have 2 2s and a 3, regardless of whichever way I order them in. So if you think of like building up this number 12 using different Legos, I have like, 2 of these kind of Legos and 1 of these kind of Legos that I need. Whether I grab them in this order or that order doesn't much matter, but I need 2 Legos of type 2 and 1 Lego of type 3 to build a structure of type 12. And again, I have a list here of the first several prime numbers. These ones go up to 30. So you can see that in the 20s, we actually only have two prime numbers. 21 is 7 times 3, 22, 2 times 11. 24 is an even number, 25 is 5 times 5, 26 is even, 27 is 9 times 3, 28 is even, and 29 is prime. So in the 20s, we're getting even a little more sparse, right? In the teens, we had 4. In the digits place, we had 4. But in the 20s, we're down to 2. So the higher our numbers get, the more sparse the primes get. So let's find a prime factorization of 36 using what we might call a tree method. What's the idea of the tree method? Well, we take the number that we're interested in, 36, and then I just ask, okay, what's a factor of 36? I mean, other than 1 in itself. Well, I could think of lots of different factors. Maybe I think of 2. That's an easy one. And then I say, okay, 36 is 2 times what? 2 times 18. And then I ask for each of these factors. Yeah, exactly. We could use 6 and 6. I could have written 6 times 6 here. I could have written 9 times 4. There's lots of different ways it could proceed. I look at each of these factors and I ask, is 2 prime? Well, yeah, actually it is. I see it in my list of primes. Is 18 prime? Well, no, it's not. It's an even number bigger than 2, so it's composite. Let me try to break 18 down. What's a factor of 18? Well, I said it was an even number, so it's got to have a factor of 2 in it. I can pull off that factor of 2. 18 I could rewrite as 2 times 9. I look at both of these numbers, these kind of leaves of the tree. If these are branches, these are kind of the leaves at this point. Well, 2 is a prime number. I'm not going to go any further with that one. Is 9 a prime number? No, it's not. I either say I don't see it in the list, 7 to 11 skips over 9, or I recognize that 9 has a factor of 3, and in fact, 9 is 3 times 3. I go to my next level. Is 3 a prime? Yes, it is. I see it in my list of primes. I know it's prime. And this 3 is as well. So 36 equals 2 times 2 times 3 times 3. So I can just start plucking off small factors if I want. I recognize the 36 is even. I can pluck off a factor of 2. I recognize that 18 is even. I can pluck off another factor of 2 until I get to an odd number, no more factors of 2 left over. Let me check for other factors, and I just immediately recognize, well, 9 is 3 times 3, so that gets me the answer. Now, as a strategic point, as you're getting better at this, when you start out, just find a factor, however you want to, whatever factor you want. But as we start getting better at this, maybe I say, okay, I know a couple of different ways that I could break 36 into the product of two numbers. Maybe I'll choose a way that where those two numbers are closer to one another, where I don't have one really small one and one really big one. Maybe I'll do like Raj suggested, say 6 times 6. That would actually probably be the best factorization to use here. So 36 is 6 times 6. But I look at these and I say, okay, are either of these prime? No. So for each of these, I'm going to go another step. So the first 6 breaks down into, well, 3 times 2 is really all that I can do there. And the second 6 also 3 times 2. And I look at each of these as 3 prime. Yes, it is. Same with 2, same with 3, same with 2. Right, I got the same 2 2s and 2 2s and 2 3s, but I only had to do kind of 2 steps down my tree instead of 3. So the more evenly I'm able to break up my numbers into factors of close size, the quicker it's going to be, the fewer steps I'll have to do in my tree, kind of on average. If you're struggling where to get started, just pick a number. If you recognize 36 is even and you can pluck off a 2, that's going to make your number a little more manageable to deal with. I can deal with 18 maybe a little more easily than 36. But if you're looking for a better strategic approach, if you can think of a couple different factorizations for that initial number, picking one where the two factors are closer together in size is usually going to be a bit more efficient than ones that are really far apart in size. And of course, if I had 36 as 2 times what, and I wasn't sure how to get this 18, well, I just do 36 divided by 2 and do my long division and get 18. So I always want to remember those skills that we built up in previous chapters and sections. They can apply here as well, of course. Okay, so let's try to find the prime factorization of 47 using the tree method. Well, 47, I'm not really sure what I have a factor of right away. I see it's not an even number, so 2 is not going to be a factor of 47. What about 3? 7 plus 4 is 11. 11 is not a multiple of 3. Since the sum of the digits is not a multiple of 3, the number itself is not going to be. 5 is the next prime number to consider. But 47 does not end in 0 or 5. So it's not a multiple of 5. What about 7? Well, I know that 7 times 6 is 42. That gets me close. 7 times 7 is 49, and now I've overshot. 2 consecutive multiples go from being below 47 to above 47. 47 is not a multiple of 7 either. 7 is not a factor of 47. And in fact, with 7 times itself is 49, which is bigger than 47. I can end my search here. In fact, I've just shown that 47 is a prime number. I guess I can come back and just kind of circle it in green. 47 is prime. So if I don't recognize a number as prime immediately, I can just kind of get rid of my tree and 47 is prime. It's just a prime number. I suppose maybe we could say its prime factorization is like 47 times 1 or something if we really wanted to write out factors, but it is just a prime number. Okay, then what about the prime factorization of I thought I had a different number here. I don't know. Prime factorization of 91 using the tree method. Yeah. Okay. Yeah, 91 will work fine. I think I started with a bigger number and then changed it because I didn't want to be here all day factoring things. So 91, again, let's look at our list of primes. Maybe I'll just actually copy it down here. So is 91 a multiple of 2? Is it an even number? No, it's not. Is it a multiple of 3? Well, 9 plus 1 is 10. 10 is not a multiple of 3. So since the sum of the digits is not a multiple of 3, the number itself is not. Is 91 a multiple of 5? It does not end in 0 or 5, so no. Is 91 a multiple of 7? We don't have a nice divisibility rule for 7, so let's just check. 91 over 7 is big enough that I can use long division. 7 goes into 9 once. 7 goes into 21 3 with 0 remainder. So 91 is 7 times 13. 7 is prime. I look at 13, what I got for the other factor, might or might not be prime, I don't know. But I actually do notice 13 in the list of prime, so 13 is also prime. So 91 is 7 times 13, that's its prime factorization. As kind of an aside, the book has this like ladder method. I find it like incredibly confusing to look at. So if we did like 36 up here, they do something like this, 36, and then divided by 2 is like 18, and then like divided by 2 is 9, divided by 3 is 3, and then like collect all of these. To me, this just like looks awful. Like, I'm like, I don't know what the heck is going on here. I mean, if you really dissect it, it kind of makes sense, but in my mind, it's a horrible abuse of notation. We're plugging the result of one operation directly into another operation, like in the same notation. That's usually very bad form. It's very difficult to keep track of what you're actually doing. So it really kind of rubs me the wrong way. I don't like this method. That being said, if this is your favorite method in the world and if it works for you, um, feel free to use it. Um, but my recommendation would be to use the tree method or to use a slightly more abstract method that we're going to talk about a little bit kind of next. Um, okay, so any questions so far? So prime numbers and prime factorizations, um, you know, sometimes it is a little bit of a grind. Sometimes there's not a quick way to go about it, and you just have to grind through the first several primes and try to see whether or not it's a factor by either a divisibility test or doing long division, and which either succeeds or fails. Um, and that's kind of unfortunately sometimes just the way that it is. Sometimes it's pretty quick to tell. Um, like up here, it wasn't too bad to keep plucking off these couple of twos and then get down to 9, which is 3 times 3. Sometimes it's a little more of a grind. Okay, so let's move into then the least common multiple. So definition, the least common multiple, abbreviated LCM, of two natural numbers, it's the smallest number for which both numbers are factors. So note that the least common multiple for two numbers is unique. Each of the individual numbers has lots of multiples, infinitely many multiples. And there are also going to be many of those multiples for number 1 versus number 2 that match, that are common multiples. But there's only one least common multiple. This is kind of an important idea. When we get to, say, working with fractions, we're going to be really interested in finding least common multiples. Now, the strategy that we'll use will work with really any common multiple. But if you just pick an arbitrary common multiple, you might be introducing really big numbers into your problem, and there's really no need to. We want to use the least common multiple because it's going to keep our problems in the future as simple as possible. Right? If I could get from kind of point A to point B in kind of a more or less straight route, or if I could get there, with some crazy circuitous route, I'd probably pick the more or less straight route. Same thing here. Why is finding the least common multiple important? Well, some of our processes we could use any common multiple, but if I use a bigger common multiple than the smallest possible one, I'm really making a whole lot more work for myself that I don't need to. Okay, so let's look at two ways of finding least common multiples. One is just by listing multiples. So let's find the LCM of 4 and 3 by listing multiples. 4 times 1 is 4, 4 times 2 is 8, 12, 16, 20, etc. And multiples of 3, 3, 6, 9, 12, 15, 18, etc. And I notice that I have a common multiple of 12. Now, had I kept going, I might have seen another common multiple, say 24. I see another common multiple. And if I keep going even further, I'd see more common multiples. I'd see more multiples of 4 and multiples of 3 that coincide. But this one is the least common multiple. It is a common multiple, and there's no other multiple lower than it that is also common. 4, the only other multiples lower than 12 are 4 and 8, and I do not see that in the list of multiples of 3, or vice versa. The only multiples of 3 that are smaller than 12 are 3, 6, and 9. I don't see any of those in the list of multiples of 4. So this is the least common multiple. It's the smallest number that's a multiple of both 3 and 4. So the answer is 12. We would often denote this by writing something like this. The LCM of 4 and 3 is 12. Note that order does not matter. The LCM of 3 and 4 is also 12. All the interchanging the order of the two numbers does, the LCM of 4 and 3 versus 3 and 4, it just like would switch the order of these columns, but that doesn't operationally change anything that we're doing looking for common multiples between the two columns. Right, this 12 matches that 12, whether this one's first and that one's second or vice versa. Let's look for the LCM of 12 and 16. So here I have 12 and 16. Now these are bigger numbers. I don't want to just start like, cranking out a bunch of multiples of 12. If I crank out 10 multiples of 12, maybe I only need 3 or 4. So 12 times 1 is 12. 16 times 1 is 16. So this is like our times 1 row. I don't see anything that matches yet. Let's multiply by 2. 24 and 32. Nothing matches between these two columns yet. 3, 36. 16 times 3 is 48. I don't think anything matches yet. 4, 12 times 4 is 48. And actually, I notice I can stop here because I have a match. Whatever I get here is going to be larger because 16 times 4 is bigger than 12 times 4. If I wanted to, I could go out and compute it out just to be sure. And now I can be really sure that anything below this line is going to be bigger than 48. And I have no other multiples in the list so far that are common and less than 48. So the LCM of 12 and 16 is 48. One thing that some people are tempted to do when finding a least common multiple, they're tempted to just find a multiple. And they're tempted to do like 12 times 16. And you can imagine, if you took 16 times 12, I mean, that's going to be a big number. I mean, 16 times 10 is 160. So you're talking about a number that's pretty close to 200-ish. Why would I want to work with a number that's like 200 when I can work with a number that's a quarter the size, 48. That's probably a much better number to work with, whatever I'm trying to do with my least common multiple, um, than, you know, a number like that. So the product of two numbers will always be a common multiple of those numbers. 12 times 16 is 16 12, so it's a multiple of 12, and it's 12 16s, it's a multiple of 16. But the product of two numbers is often not the least common multiple. We can often do a lot better than that. So listing multiples, okay, for smaller numbers, it works pretty nicely, but it's kind of a lot of work, right? I mean, what if 12 and 16, what if instead this was like 13 and 16, the LCM of 13 and 16? I'd be writing out multiples all day. That would be a pretty big LCM just because those numbers don't mesh as nicely as these ones do. And I'd be doing a lot of work writing out a bunch of multiples. Can I find a strategy that's more efficient, that scales a little bit better, that if I have a problem that doesn't work out so nicely as these first couple here, that either has maybe bigger numbers or numbers that don't mesh as nicely as say 12 and 16 do, can I find a strategy that generalizes a little bit more nicely? And that strategy is the prime factorization method. So the first thing we're going to do is find the prime factorization of each number. We're going to figure out what building blocks do I need to build each of the two numbers that are my inputs into this LCM. Then I write each number as a product of primes. And then I basically match up the primes, which we'll see kind of in a second what I mean by that. And then we multiply all of our factors. So the first thing we want to start with is taking our two numbers and finding their prime factorizations. Well, 4, I can factor it into 2 times 2. And then 3, well, 3 is already prime. So I just want to write it over here as a 3, but I want to match my primes vertically. So I don't want to write this 3 like under the 2. I'm going to kind of slot it in off to the side here to the right of the second 2. So this way I have kind of one column for this 2, one column for that for the second 2, and a column for the first 3. So what I can think of is, roughly speaking, like 4 needs like 2 of these Lego pieces to build it. 3 needs this Lego piece to build it. So to build both of them, if I wanted to give you a Lego set that you could use to build both 4 and 3, that would need to include 2, another 2, and a 3. You could use these two 2s to build your 4, and you could use this 3 to build your 3, and the Lego set that I provided to you is the smallest Lego set I could provide, the smallest number of Legos that I could provide, that allows you to build both of the numbers 4 and 3. So 2 times 2 times 3 is 4 times 3, or 12. So it turns out that in a simple problem like this, the least common multiple ends up being the product of the two numbers. In other words, my kind of blue Legos didn't help contribute at all to building the 4, and my green Legos didn't contribute at all to building the 3. I might as well have just given you 2 separate Lego sets. But that's not always the case. So let's look at 12 and 16. I'm going to write 16 first. And we'll start off by writing their prime factorizations. 16, I see it's 2 times 8, but I also see it's 4 times 4. Let me use that factorization because 4 and 4 are closer together than 2 and 8 are. Although it's not the end of the world if you use 2 and 8, you'd still get to the same place. I look at each of my 4s. Are they prime numbers? Nope. So I keep breaking them down. 4 is 2 times 2, as is the other 4, and these are my prime factors. So 16's prime factorization is 2 times 2 times 2 times 2, 4 factors of 2. 12's prime factorization, I know 12 is 3 times 4, and 3 is prime, so that's one that's completed. 4 is 2 times 2, and those are both prime. So for 12, I'm going to write it as 2 times 2. And then I'm going to jump over here. I don't see any other 3's above in the 16 factorization, so I'm going to jump off to the right and make a new kind of column, so to speak, for 3. So I have 2, a second 2, a third and a fourth 2, and a 3. It's so strange. If I'm thinking of a number and saying a different number, I like always write the one that I'm saying, but not the one I'm thinking. So when I was saying the fourth 2 and I'm about to write a 3, I wrote a 4. I think it's just an interesting psychology thing. So kind of roughly speaking, what am I saying here? I'm saying if I wanted to provide to you a Lego set that has the fewest number of Legos, but you could use those Legos to build a 16, or you could use them to build a 12, I could give you 4 2's and 1 3. You could choose to use 2 of the 2's and the 3 to build a 12, or you could use the 4 2's and forget about the 3, and you could build the 16. You can't build the 12 and the 16 at the same time. So if I had come up with a common multiple of 12 times 16, that would be like giving you enough Legos to make the 12 and the 16 at the same time. But usually we don't need to do that, especially for the types of problems that we'll be really using this a lot for in the near future. We don't need to be able to like build a 12 and a 16 out of the Lego set at the same time. We just want to know that we have enough Legos that if we wanted to, we could build a 12, or we could tear that down and we have enough that we could build a 16 separately. Uh, I would need to use some of the Legos from the 12 to build the 16, or some from the 16 to build the 12. I can't build both numbers at the same time out of the same set, but this is the minimal Lego set, so to speak, that I need to be given to build a 12 and also to build a 16 kind of at 2 separate times. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 3 is 48. Now, what's the main advantage over this approach compared to the listing multiples approach? The listing multiples approach, in a sense, the more work that I do, the bigger the numbers get. I kind of like, just keep increasing complexity over time before I get to decrease complexity a little bit. Right, and then I can decrease a little bit. Over here, the first thing that I do is I break my bigger numbers down into the smallest numbers I can. I kind of like decrease complexity first before building it back up to the necessary level. And this is how I like to do math. I would much rather take a problem, decrease complexity as much as I can. Maybe that means in an expression, simplifying the expression and combining like terms, decrease the complexity, and then do something. Do maybe an equation solving step, and then simplify again, decrease the complexity again. I'd rather deal with lower complexity structures than higher complexity structures. And that's why this might be a better method to use in general. The first thing that I'm doing is kind of taking this big, complicated Lego structure and breaking it down into its component blocks, instead of taking like a big Lego structure and trying to glob on more and more and more of those structures. Okay, let's try to find the LCM of 28 and 40. This is one that I probably would not want to do by the multiples method. I think it's just going to take quite a while, and I'm going to have to do a bunch of multiplications. Okay, so let's find a prime factorization of 28. Well, I know that 28 is 7 times 4. It's not the end of the world if you picked 14 times 2. It might just take you an extra step going down the tree here. But actually, it wouldn't even take you an extra step if you went that direction. So 4 is 2 times 2. So I see that my prime factorization of 28 is 2 times 2 times 7. What's my prime factorization of 40? I might recognize this as, say, like 5 times 8, or I might recognize this as 10 times 4. I think it's probably a toss-up which one you use. This one's a little bit faster. 5 times 2 and 2 times 2. So I see I need 3 factors of 2, 1 factor of 5. Here's 1 factor of 2 and a second. I don't want to write the next factor of 2 right under the 7, so I'll jump over to another column. There's my third factor of 2. I need a factor of 5 as well. That doesn't mesh with the 7 either, so I'll write it in a new column. And now I can bring down these columns. So my least common multiple is this product, 2 times 2 times 7 times 2 times 5. I do recognize 5 times 2 is 10, and 2 times 2 is 4. So 4 times 7 is 28, times 10 is 280. So my LCM of 28 and 40 is 280. I notice that I can use like these two 2s and this 2 and this 5, those Lego pieces, so to speak, to build the 40. Or I could tear the 40 apart and use these two 2s and the 7 to build a 28. So this is the smallest set of Legos, so to speak, that I could give you that you could build a 28, or you could tear that apart and build a 40 as well. Right. I definitely wouldn't want to deal with the common multiple of 28 times 40. That's going to be a pretty big number, like close to 1,000. It's a much larger number than what I need to deal with, 280. That's already a kind of pretty big number. I don't want to make it any bigger than it needs to be. Any questions so far? Any questions on anything in chapter 2? Okay, let's jump into chapter 3 then. So we've got about a half an hour or so left to get through 3.1, and 3.1 is just kind of an assortment of different ideas related to integers. The first thing that I want to do is we're introducing this idea of integers, we're introducing this idea of a new number system, or really an expanded number system. So the question is, why do we need to expand our number system in the first place? One answer might be we want to model things with this bigger expanded number system. And that's a fair answer, but there's an even more basic reason. We've already seen how to solve equations using the addition and subtraction property of equality, that we can add or subtract the same thing to both sides. So if I have, x plus 3 equals 5, I subtract 3 from both sides, 5 minus 3, x equals 2. I can solve this equation. I can solve x plus n equals m by subtracting n from both sides. And it seems like I can solve this for any case where n and m are natural numbers. It would seem like that at first. But what if I had a very similar looking x plus 5 equals 3? What natural number can I add to 5 to get 3? 1 plus 5 is 6, 2 plus 5 is 7, 3 plus 5 is 8. There's no natural number solution. So I can solve an equation like this, but I cannot solve an equation like this that looks very, very similar if I just stick to natural numbers, 1, 2, 3, 4, 5, or even whole numbers for that matter, 0, 1, 2, 3, 4, 5. So if I have an equation like x plus n equals m, where m and n are natural numbers, unfortunately, I might or might not be able to solve this if I force x to stay a natural number. So x, I'll just say equals natural number, and I'll put a big question mark here. What I would like to do is I would like to expand my number system, expand my view away from natural and whole numbers, build out some more numbers, so that way I can solve any equation of this type. So that way I can, for instance, solve x plus 5 equals 3. And I think we probably know the solution is like x equals -2, right? So we need kind of the negatives of the natural numbers. We need to be able to consider those as well. We need to expand our number system to include negative numbers. And that's what leads to the introduction of the integer number system. Okay, so our goal here really is to expand our consideration from chapter 1. We were dealing with just whole numbers and natural numbers, just the positives or non-negatives. We want to expand our vision to allow negative numbers as well. So let's take a look at the number line. And we think of our number line as having positive numbers on the right, 0 kind of in the middle, negative numbers on the left. And really importantly, this is kind of like a mirror image, or kind of like a opening a book kind of. That the number, say like 2 is here, and the number -2 is over here. So 2 is like 2 units to the right of 0. -2 is 2 units to the left of 0. Or for instance, 3 is 3 units to the right of 0, and -3 is 3 units to the left of 0. This can be a little bit confusing because, for instance, 3 is bigger than 2, but -3, well, -3 is to the left of -2. -3 is less than -2. So kind of an important point here. The ordering of our positive and negative numbers kind of changes, right? When we flip over the 0 delineator here between the positives and the negatives. Another way to think of it is, if you think financially, positive numbers might be like dollars you have in your pocket, and negative numbers might be money that you owe on maybe a car loan or a student loan or something like that. So if I have $4 in my pocket and I get more dollars, if I have $6, like I have more money. if I start off owing $2 and then I owe $3, I owe more money, but I kind of like have less money in aggregate, right? If I have $4 in my pocket and I owe $2, I have kind of a net positive of $2. If I have $4 in my pocket and I owe $3, I have net less money. I have net positive of $1. So I can maybe think of the positive numbers representing kind of assets or things that I own, and negative numbers representing debts or things that I owe. That's kind of a common way to talk about it is, what you own minus what you owe is net worth. So that's one way that I like to kind of think of this. And I have to be a little careful again, because, if I see -3 and -2, my brain might automatically jump to that, oh, 3 is bigger than 2, so -3 is bigger than -2. But remember, it works the opposite way on the opposite side of 0. It's like a mirror world, not just like the same thing shifted over to the left. So let's list these following numbers in increasing order. Well, one thing that I like to do is maybe I'll start with 0. I know that 0 kind of serves as like an anchor point, and I know that all of the negative numbers are less than 0, and I know all of the positive numbers are bigger than 0. So 0 I know is going to be right here in the middle. Then maybe I'll kind of separate out my positive numbers. So what are they going to be? 3, 6, 2, and 4. I know they're all going to be to the right of 0. And my negative numbers, -1, -5, -3, are going to be to the left of 0. My positive numbers aren't too hard to order. 2, 3, 4, and 6. I don't think that's a big deal. But my negative numbers, again, I have to be really careful. Between -1, -3, and -5, -1 is actually the furthest to the right of those three. So -1 is going to the left of 0. It's the first one that I write going to the left of 0. Then -3, then -5. So this is in increasing order. So -5 is less than -3. I kind of have more money to my name if I only owe $3 instead of owing $5. -1 is bigger than -3. 0 is bigger than -1. 2 is bigger than 0. 3 is bigger than 2, and so on. Okay, so opposites. We call a number the opposite of another number if it has the same distance from 0 on the number line, but is on the other side of 0. And we note that opposites are what we get when we switch the sign, SIGN, in front of the number. So for instance, the opposite of 2 I see that 2 is 2 units above 0. If I go 2 units below 0, or if I just kind of take the mirror image of 2, the opposite of 2 is -2. But I also note that if maybe I'm looking at -4, it's 4 units below 0. Its mirror image is going to be +4. Sometimes if I want to really be explicit, I'll write like a plus in front. That's probably not technically best practice. That's probably not the best notation. But if I want to be very clear, sometimes I'll write that. But here where we're trying to be really careful about notation, I'll try to refrain from doing that. So sometimes switching the sign means a negative sign basically goes away, or no sign turns into a negative sign. Or if I just have, say, a number that I represent with A, its opposite is negative A. So if the opposite of A is negative A, note that that means that, so like the opposite of 2 is negative 2, that kind of makes sense, but the opposite of negative 4 is negative of negative 4. But wait, so a negative of a negative number is a positive. Each time I kind of append another negative to the front, I flip over 0. So let me erase this over here. So if I start here at 4, if I change 4 to negative 4, that tells me flip over 0. Let me actually use one that's a little closer so I don't have to write as much. But we'll go with 2. So here's 2. If I apply a negative, that brings me down to negative 2. It says flip over the 0 point. If I apply another negative to get negative of negative 2, the opposite of negative 2, I flip over again and I'm back at positive 2. If I have negative of negative 2, I'm back at negative 2. But I see that negative of negative 2, the opposite of 2 is 2. Okay, so what are the integers? The integers are another number system. They're another set of numbers. We talked about the natural numbers and the whole numbers. The integers are the natural numbers, aka the counting numbers, their opposites, and 0. So the natural numbers, sometimes we represent the natural numbers, sometimes we give them the name, kind of like bold N for natural numbers. Those are the numbers. Oh, should not include 0 in there. Those are the numbers 1, 2, 3, etc. 1, 2, 3, 4, 5, and so on. The integers include the natural numbers, as well as 0, as well as all the opposites of the natural numbers. So 1 gets its opposite included, negative 1. 2 gets its opposite included, negative 2, and so on. As kind of a little side note, we sometimes refer to the natural numbers using bold Z. And you might say, we refer to the integers using bold Z. I think I said natural numbers. We refer to the integers using bold Z. And you might say, where does Z come from for the integers? That's kind of strange. Well, Z is for the German word Zahlen, meaning number. So that's where that Z comes from. I'm not 100% sure why they didn't use I, but we tend to use I for a lot of other things as well, especially like bold I and stuff. So my guess is that because in some more advanced math, we use kind of this like bold I to mean a couple other things. They probably didn't want confusion with that. Or maybe it was the Germans who, you know, got there first and got to name it, and they named it Z, and everybody just fell in line behind them. So I know we don't think of Germany as necessarily like the height of academics these days, but there was a time, in the definitely 1800s, maybe 1700s, maybe a little bit before that as well, where I mean Germany was like, the height of the academic world for quite a while. So a lot of those guys like Freud and Jung and who like Nietzsche, I think, yeah, he was German. I mean, so many of these philosophers like Hegel and I think Marx was German, or at least something close to German. So there were a couple hundred years where Germany had a huge influence on a lot of mathematics and philosophy and a lot of the different academic areas. But I digress. Okay, and then the last kind of thing that we're going to talk about is the idea of an absolute value. So absolute value, the definition is that the absolute value of a number is its distance from zero on the number line. So it's kind of like an absolute distance. This might be a little bit of like a circular definition, but if I go from 0 to like -2, if I say I'm going in a direction to the left, that might be kind of the direction I'm heading. But how far do I go? I go 2 units. So in absolute units, not relative to like if I was pointing this way, I have to walk backwards 2 units. That would be like a relative direction relative to pointing in the positive direction. You have to walk backwards 2 units. But in an absolute direction, if I'm pointing this direction, if I'm pointing to the left, in absolute units, I have to walk 2 units the direction that I'm headed. So that's why the word absolute is in there. At least that's my interpretation of it. So, sorry, my neighbor is texting me. They're going to New York and she's an older lady and they always get a bit kerfuffled whenever they leave and they want to make sure all the mail is, not piling up and all that kind of stuff. Um, so, but anyway, so the absolute value is that absolute distance. It's the distance from 0 on the number line. Oh, yeah. So note that the absolute value, well, it's denoted with these 2 vertical lines. So like absolute n. And we would say the absolute value of n, or if I'm being lazy, I'll just say absolute n. Note that the absolute value of n is bigger than or equal to 0 for all numbers. If I take any 2 points on the number line, when I'm looking for the absolute value, I'm only looking for the distance between those 2 points, not the signed distance, but just that distance. I'm not going like from the left point to the right point or from the right to the left. I'm just saying, what's the distance between these, right? What's the distance between Pittsburgh and Chicago? Whatever, 650 miles or whatever it happens to be. Probably not that far, but whatever it happens to be, right? I don't say it's negative 650 miles sometimes and positive other times. So I'm just looking at the distance between 2 points. And of course, the closest that 2 points can be on the line is if they're the same point. So for instance, the absolute value of 20, here's 0, here's 20. 20 is 20 units away from 0. So the absolute value of a positive number is just that number. The absolute value of, say, -19, here's 0, here's -19. The distance between these 2 points is 19 units. So the absolute value of a negative number is positive of that same number. It's the opposite of that number. So if we're taking the absolute value of a number, we can come up with a rule that says if the number on the inside is positive or 0, the absolute value just goes away, basically. The absolute value of the number is just the number if the input is positive or 0. If the number inside the absolute values is negative, we take its opposite. We just make it positive. Or in other words, the absolute value symbols just make whatever's inside of them not negative. We could also look at something like this, absolute value of 9 minus 6. And actually, this note should be here, not there. So if we look at, for instance, absolute value of 9 minus 6, we have a bit of a question here. How should I parse this, right? What does this list of symbols mean? I know that an absolute value applied to a single number, I know how to deal with that. But is this like absolute value of 9 minus absolute value of 6, or how should I do this? Do I do subtraction before absolute valuing or whatever? Well, absolute value is considered a grouping symbol like parentheses or brackets or curly braces. So it has a part of its characteristic is that it's a grouping symbol. Another part of its characteristic is that it makes everything positive. Where, say, parentheses are a grouping symbol, but they don't affect the sign of the thing inside. So what that means is I do the inside first. I say 9 minus 6 is 3. Now that I've simplified the inside, now I take the absolute value of 3, which is 3. If I looked at something like this, actually at first glance, this can look really confusing. It's like, am I taking the absolute value of the negative sign here or what? We have to be really careful when we have multiple absolute values. When we have parentheses, they kind of at least like point in a certain direction, but absolute values don't. So we have to be careful when we're parsing this. And I see a first absolute value sign combined with a second one. So that's one grouping. And then this third absolute value sign combines with that fourth one. So that's another grouping. It would not make sense for me to consider these absolute value signs as like outer absolute values and these as inners, because what would be inside of these absolute values? Just a negative sign, just a minus sign. I can't take like absolute value of minus. That doesn't make sense. If I had nested absolute values, like if I had absolute value of 17 minus whatever, absolute value of 8 minus 2, I don't know, let's say plus 3 or something, I might have to, in some cases, be very careful about uh, how I write this and make it very clear which absolute values are inside or outside or whatever. So there could be some cases where there's some ambiguity, but here there's no ambiguity. So I need to do the first one first. 17 minus 8 is 9. That's inside of absolute values. Minus 14 minus 6 is 8 inside absolute values. So I basically like have two parentheses here, so to speak, and I've simplified the inside of them as much as I can. Now I look at absolute value of 9. Well, 9 is a positive number. Its absolute value is just itself. Then minus. And then for the second term, absolute value of 8, well, 8 is a positive number. The absolute value is just leave it alone. And 9 minus 8 is 1. So this looked really complicated to start with, but taking it step by step, we get the answer. And we're pretty much perfect on time because we're going to get through part E and then call it a day. So here's another example that can look pretty complicated, right? If I'm just looking at this, there's a lot of symbols here. So I've got to start collecting symbols, especially grouping symbols. Okay, I see my absolute values here. My beginning and end of the absolute values begins just before the -2 and ends just after the -2. I have parentheses here. So they're also another grouping symbol. So what do I have? I have 6 times 13 minus 4. And I might actually, I omitted the operation here. This is 4 times the absolute value of -2, but I actually might make that explicit. Maybe I'll put it in there because it makes it a little easier for me to read. I'm less likely to get confused about that if I explicitly put that times back in. And now I know that I want to probably start on the inside. Again, there's kind of a couple different ways you could approach when you have nested grouping symbols. But now that we're a little bit more used to working with order of operations, we'll kind of start with our innermost grouping symbols. Absolute value of -2. Well, that's a negative number getting plugged into an absolute value. We take its opposite. We make it +2. Everything else just stays the same. Now I have some parentheses that I want to do first. The parentheses bumps that set of operations up to the top of the order of operations. And so I want to figure out what is 13 minus 4 times 2. Right? That's the first thing that I want to do before I do the 6 times. And here I have multiplication first. 4 times 2 is 8. Multiplication gets done before subtraction. Still inside the parentheses, so the subtraction inside the parentheses gets done next. And now I have 6 times 5. And I could even get rid of the parentheses at this point if I wanted to, or 6 times 5 is just 30. So again, this looked very complicated to start with. We took a couple seconds, 30 seconds or so to kind of parse everything to say, what is all of this syntax, basically, what all of these symbols, what do they mean in this context? Where is the start and end of my absolute values? Where's the beginning and end of my parentheses and so on? And then just chipped away at it step by step. Took a few steps, but each step wasn't that bad, especially when we figured out where all of our grouping symbols start and end. So are there any questions on anything we talked about today? Anything else? Okay, then I'm going to stop the recording.